Welcome to Gurukul Live Lectures. Myself, Dr. Preeti Japani, Assistant Professor, Department of Computer Science, Aribhat College, University of Delhi. Today I am here to present a lecture on data structure, which is the second lecture in the series. So, today we are going to discuss about some linear data structures, basically stacks and queues. So, the agenda or the today's lecture plan will be, we will be looking at what is linear data structures, then we will be going through stacks in detail considering its applications, operations and implementations, then which is followed by queues considering its applications, operations and implementations again. Then we will see the problem with linear implementation of queues, and then we will look for the solution, which is circular queues, and then we will go through implementation of circular queues. So, data structures basically are of two types, one is linear, another one is non-linear. So, linear data structure comprises of stacks, queues, arrays, lists and many others, while non-linear data structures are graphs and trees. So, the list is not exhaustive, there can be many other examples. So, in today's lectures we will be considering stacks and queues. But first of all, what is a linear data structure? In the linear data structure, elements are arranged in the form of a sequence, which is a kind of an orderly manner. Elements are placed in continuous memory locations one after the another. And what are the operations which can be performed on linear data structure? Commonly these operations are traversal. So, traversal is accessing the elements of that data structure one by one, searching for a particular element, that whether that element is present in the data structure or not. We can insert some new elements in the data structure, or we can delete some already existing elements. We can sort the elements in a particular order, whether it is ascending, descending or any other order, or we can also merge two similar linear data structures. So, this is the list of operations which are commonly performed on a linear data structure. In the list of linear data structures, the first data structure which is very popular and very much useful is stack. So, what is a stack? A stack, you can say, it is basically a pile of elements. As you can see in the figure, it is a pile of books, you can say, or a pile of plates. So, a pile of elements. Now, these elements can be integer type or character type or whatever type they can be. Basically, it is a LIFO structure. LIFO structure means last in, first out. Ordered, it is an ordered list of n elements where n is greater than 0, n is always greater than 0, and all insertion and deletions are made at one end called the top. So, LIFO structure here means the elements which are inserted first will be taken out last. So, last in, first out. Common operations which can be performed on this stack are push, pop, peek, or it can be also known as top, is empty, is full. Is full is only for static allocation. I will be coming to static allocation in a minute, and then size. So, what are the applications? This stack data structure is actually a very useful data structure within the computer world. Whether it is addition of two large numbers, it is conversion of infix to postfix, or evaluation of postfix expressions, or you need to know balancing of whether the symbols in a particular expression are balanced or not. All these are the applications which are based on stacks. All these applications use stack, and recursion is one of the example which is very commonly used. So, recursion is based on stack. So, stack can be implemented either using arrays, which is called static implementation or static allocation, which I was just talking about, or it can be implemented using linked list. So, using arrays, it will be a static implementation. Using linked list, it will be a dynamic implementation. So, in today's lecture we will be focusing upon the array implementation of stacks. So, array implementation of stack consists of following operations. One is push. Push means pushing or storing an element on top of the stack. Pop means removing or accessing the element from the stack. And to implement this push and pop push and pop operations, some subordinate operations are also required, which are peek, is full and is empty. So, peek is just to get the top data element of the stack without removing it, it is just displaying or just accessing the topmost element. Is full is to check whether a stack is full or not, or whether it is having a capacity to, or it is having a room to insert new element. Is empty is to check whether the stack is empty. If the stack is empty, we won't be able to take out any element further. For all these operations, a pointer top is maintained to keep a track of last items which is stored onto the stack, which is pushed onto the stack. In case of empty stack or initially, we need to initialize the top pointer to -1. So, when we start with the stack, our top pointer will be -1 and then gradually it will change its own value depending upon whether an element is pushed, which is to be inserted into the stack, or whether the element is popped out from the stack, which is deletion of that particular element. So, considering the subordinate operations which are peek, is full and is empty, let us go through their pseudocode once. So, is empty is an kind of procedure or a kind of function which is going to return a boolean value kind of, you can say true or false, 0 or 1. So, if the value of top equals to -1, then it will return true. That means the stack is empty, it is not having any element into it, else it will return false. So, if top is having any value other than -1, the procedure will return false. So, top equals to -1 means the stack is empty. Then the next one is full. So, now we are looking at the array implementation of the stack. So, max size is the maximum size, is the size of the array. So, if top equals to max size, then this procedure will return true. That means your stack is already full and you cannot insert any other element onto the stack, or you cannot push any element onto the stack. And if top value is not equals to max size, then it is going to return false, which indicates that yes, there is a room to push the element onto the stack. Peek is another function which is going to return the top of the array stack. So, stack here is an array and it is going to return the topmost element which is given by the index top. So, these are the subordinate functions which are required for push and pop operations of stack. So, push operations, as you can see on the screen, let us say our stack is initially empty and we pushed an element A, then we pushed an element B, then we pushed an element C and then D, and then finally an element E is pushed. So, before pushing E, our top is at D, then E is pushed onto it and top is being incremented to point to this latest element which is being pushed. So, this is actually push operation. Before the push operation, before any of the push operation, when stack is empty, our top is equals to -1 and then top keeps on incrementing every time we push an element. So, pushing is, as I have told you, is inserting a new element onto the stack. So, before pushing the element onto the stack, we need to check whether the stack is full. If the stack is full, this condition is known as overflow condition. This must produce an overflow error and then it should exit, because there is no room to push your element onto the stack. if stack is not full, that means it is having some room. Increment the top to point to the next empty space as it is done in the previous figure. So, top earlier was pointing towards D, and as it is having some room, so it will point towards the next empty step, next empty space, and then onto that particular empty space where top is pointing now, after increment we are going to add the data element to that particular stack location. And if we are succeeding in adding the element, in pushing the element, or in storing the element onto the stack, this is going to return the success status. So, push, basically let us consider an stack which is of data type integer. So, push, within push we need to within this push procedure we need to pass on the value which we need to store onto the array. That means that data or that particular element which we want to push is to be given to this push procedure as it is clear on the screen. And before pushing, we need to check whether if it is full or not. If it is full, then it will print stack overflow and we need to exit. So, here is a pseudocode for this push procedure. If it is not full, if is full is going to return you false, then you need to increment the top, which will be done by top is equals to top plus 1, and then the data which is passed as a parameter to the procedure push is stored or is initialized onto the top element of this stack array, which is achieved by stack top is equals to data. So, that means data has been pushed, as in the similar manner E has been pushed onto the stack as shown in the previous figure. Otherwise, it will print the stack overflow status and it get exit. So, this is the push operation of the stack. Now, coming to the pop operation. Pop operation, let us consider the stack having elements A, B, C, D and E, where top is pointing towards E. Now, we need to decrement the top to the next to the position below that position, below the whatever the original value was top, whatever the original value of top were, and then we need to take out that particular element. So, essentially taking out that element in array is a hassleful thing unless we are implementing it dynamically. So, we just decrement the value of top and let the element be at their particular position. A new element coming to the position will be overwriting the element which we want to delete. So, physically we need not to delete the element from the array, we just decrement the value of top, and when again we want to push an element, then we need to increment the top and the new element will overwrite the previous one. So, pop basically is accessing the content while removing it, we can say symbolically, yes, while removing it from the stack is known as a pop operation. A pop operation involves the following step. This includes first to check whether the stack is empty or not. If a stack is empty, that means it is not having any element to be popped out. We need to signal an error, and that error is known as underflow error. So, we need to check that whether a stack is in the underflow condition. If yes, then we need to exit. If a stack is not in the underflow condition, that means it is not empty, having some elements. We need to access the data element at which the top is pointing presently, and then we decrease the value of top by 1. Again, we need not to physically remove the element, we just access that particular data element, return it if it required through the pop through the pop operation, and then we decrease the value of top by 1, and if we are succeeded, our flag will be returned or flag will be returned at success. So, in the array implementation of pop operation, data element is not actually removed. So, instead top is decremented to a lower position in the stack to point to the previous value, you can say. So, in case of pop, it is going to return an integer data. It will check first whether it is an empty stack or not. If it is an empty stack, then whatever is if it is an empty stack, then it will give stack underflow error. If it is not an empty stack, then it will return the value into that data element, which will be the value of the topmost element on which top is pointing. Then it will decrement the top to top minus 1, and that data will be returned into that integer value. So, essentially we are just accessing the value which is available on the top position, and then we are decrementing the value of top or the index top. So, what are the advantages of array implementation of stack? As I have already told you, there is one more you can say implementation of stack, which is linked list implementation. Here we have discussed array implementation. So, array implementation of stack is actually easy to implement, and memory is saved as pointers are not involved, because linked list implementation includes pointers, a heavy use of pointers. So, pointer itself is actually a memory location that itself going to take some memory. So, memory will be given to the pointers also. And again, the next advantage is array implementation is always easier to implement, because what we need to take care of is just an array and one index, which is top. Coming to the disadvantages of the array implementation of stacks, array implementation of the stacks is not dynamic. If not dynamic, that means of course it is an static implementation. A static implementation says, let us say I have defined an array of size 100, and that stack is having that size, max size as 100. So, if I need more elements, then obviously I won't be able to expand that array at runtime if needed. Similarly, on the other hand, let us say I am requiring only 25 elements of that particular array, not the 100 elements. So, that 75 space of 75 elements will be obviously wastage. So, it is not going to grow and shrink depending upon the application needs at runtime. So, that is what the disadvantage of the static implementation or the array implementation of stack is. But yes, on the contrary, it is easier to implement, and memory which is given to the pointers, or memory which will be taken by the pointers in case of linked list implementation, or you can say your dynamic implementation, will of course be saved. So, depending upon what our application needs, whether we are looking for more dynamism into the application, or we are looking for easiness of implementation, we can choose whatever idea of implementation we need. So, both the ideas as array implementation as well as linked list implementation, which is dynamic one, array implementation which is a static one, is having pros and cons both the ways. So, depending upon the need of application, we can choose whatever we want to. Coming to the next data structure, which is queue. Queue is also a linear data structure. Elements are arranged inside the memory in continuous locations, one after the another in a particular order. Element is inserted from one end, which is called rear. It is also called the tail end, and the removal of existing element takes place from the other end, which is called front end, or also called head. So, this is very much similar to a kind of, you can say, real life queue implementation, which is based on first in first out principle. One which is entering into the queue first will be taken out first, and one which is entering into the queue last will be taken out last. So, basically this is first in first out data structure, which means that elements inserted first will be obviously removed first or accessed first. So, this is very well similar to the real life implementation of queues. Now, as you can see on the screen, there are two ends, one is back end, another one is front end. From front end we can dequeue the element, we can take out the element, and from the back end we can enqueue the element, that means we can insert the element. So, insertion of element inside the queue or into the queue is known as enqueue operation, while taking out the element from queue is known as dequeuing the element. So, now we have two ends, one is back, another one is front, one to enqueue the element, one to insert the element, another one to dequeue the element to take out the element. So, as we have seen some operations like push and pop within the stack also. So, what is the difference between a stack and a queue? Unlike a stack, a queue is open at both of its ends. One end is always used to insert the data, to enqueue the data, other is used to remove the data, that is to dequeue the data. Queue always follow first in first out methodology, that is data item stored first will be accessed first, while your stack follows last in first out methodology. So, we can say in short we can say queue is a FIFO structure, it is a FCFS structure which is first come first serve, and on the other hand stack is a LIFO structure which is last in first out. So, the difference between stacks and queue is in removing the element, the way we remove the element or methodology to remove the elements. In the stack we remove the item which is most recently added, will be taken out first on the basis of last in first out LIFO principle, and in the queue we remove the item which is least recently added, which is first in first out. So, what are the applications of this queue data structure? Queue data structures is also a very commonly used data structure. If we need to implement some CPU task scheduling like round robin queue or first come first serve queue or priority basis queue, then queue data structure is very useful. Or we need to serve the request on a single shared resource like printer maybe, then also queue data structure is needed to be implemented. Call center phone system, let us say we are calling to a particular call center and it is saying us that please wait, we are going to connect to the next available representative. So, that is also basically a queue in which a request has been put up. So, call center phone system uses queues to hold people, calling them in an order until a service representative is free. Or traffic queue is also similar, traffic queue or simulation of traffic queues also uses this queue data structure. Also handling of interrupts in real time system, the interrupts are handled in the same order as they arrive, that is first come first serve. So, as stacks, queue is also a very popular and a very useful data structure. So, on the same grounds as we have gone through stacks, we will be considering array implementation of queues here, not the linked list implementation Only the array implementation, which is a static implementation, we are considering here in this lecture. So, operations, major operations on Q are NQ and DQ. As we have seen, the major operations on Q stack were push and pop. Similarly, here they are NQ and DQ. So, NQ is nothing but adding an item to the queue, but for that we need to check whether the queue is full. If it is full, that means it is in the condition of overflow. We cannot insert more elements into it, that we need to check. Or we can say DQ. DQ is removing an item from the queue, that is the second most popular, second most useful, we can say, operation on the queue. It is actually items are taken out in the same order in which they are inserted. If the queue is empty, to implement the DQ operation, we need to check for the underflow condition. Underflow condition says queue is empty. If the queue is empty, then we cannot DQ any element from it, and we can say that the queue is empty and it is in the condition of underflow. So, in order to implement the NQ and DQ operation, two pointers will be required. One is front, another one is rear. Front pointer is required to get the front item from the queue, to take out the front item from the queue, and the rear pointer is required to get the last item from the queue. Now, in order to implement NQ and DQ operation, not only these two pointers, but some of the subordinate functions are also required, as they were required in case of stacks we have seen. One is peek, which is to get the element at the front of the queue, but without removing it. That means we are just accessing that particular element, we are not DQing, we are not removing that element. Another subordinate operation which is required is full, to check whether the queue is full or not. If the queue is full, then you won't be able to enter any element into it, or you won't be able to NQ any element into it. Another operation which is required is empty, which is checking if the queue is empty. So, if queue is empty, we will be not able to take out any element from it. So, is full and is empty, these both the operations are returning bool values. Now, here is implementation wise, we can say queue as stacks can be used using array or using linked list, and the interesting thing here is a queue can be implemented using two stacks also. So, there are n number of ways, or we can say there are 3 number of common ways through which a queue can be implemented. One is array, another one is linked list, and third using multiple stacks or two stacks we can say. But the easiest way of implementing the queue is using an array. So, we will be focusing on the array implementation of queue as we did for stack. So, initially the head, which is the front pointer, and the tail, which is the rear pointer of the queue, both points at the first index of the array, or we can say both points the starting index of the array, which is 0. As we keep on adding elements to the queue, the rear or the tail pointer keeps on moving ahead, and it will always point to the position where the next element will be inserted, and head pointer is moved when the elements are taken out, when the elements are DQ'd. So, when we insert the elements, we work with tail pointers, and when we take out the elements, we work with head pointer or front pointer we can say. And for implementing queue, we need to keep a track of two indices, front and rear. Rear is used to NQ an item, while front is used to DQ an item because we are taking out the item from the front and we are inserting the item on the rear side as it is done in the real queues, you can say. So, some functions which are required, which are subordinate functions and are required for NQ and DQing operations are, one of them is peek. So, peek function is going to return an integer value if the q, assuming that q is of integers. So, q here is an array and it is returning the front, the element which is available at the front index of the queue. So, it is returning q front. So, this function helps to access the data which is available at the front of the queue. Now, as we are using single dimensional array presently, which is, you can say, a linear implementation of queue, it is not the circular implementation of the queue. I will be coming to the circular implementation in the later part of the lecture. Only for single dimension array, only rear pointer or only tail pointer is needed to be checked for is full method, while for the circular implementation, which we will be covering soon, real pointer as well as front pointer both are needed to be checked for is full condition. So, is full method will check whether the rear pointer is reaching at the max size of the maximum size of the array to determine whether that queue is full or not. It is an method which is, as I have already told you, which is returning either true or false. So, as we are implementing array in which the commonly used starting index is 0. So, if it is an array of, let us say, 8 elements, the elements will be indexed from 0 to 7. So, if all the elements from 0 to 7 are filled, that means our rear is at the max size minus 1. Here in the example it is 8 minus 1, which is 7. So, if rear is pointing towards the last element, that means all the elements are full and the queue is full. So, this condition will return true, else it is going to return false if rear is not equals to max size minus 1. Coming to the next, which is empty function, checking for the underflow condition, whether the queue is empty. If empty, it is known as underflow. So, if the value of front is less than 0, it tells that queue is not yet initialized, hence it is empty. So, if front is less than 0 or front is greater than rear. So, how can this front is greater than rear? I will be coming up to it into a minute. If front is less than 0, return true, else return false. So, this is the you can say pseudo code for is empty function is, which will return true if front is less than 0, that means there are no elements to be DQ'd, or it will return false. So, you can see here in this picture, if we are going to say NQ. So, NQ, it is having one element. So, the situation before NQing is it is having elements A, B, C, and then we need to NQ the element D. So, the rear pointer is incremented and D is inserted into the array, while front is kept as it is, because we are NQing the elements. So, we will be working with rear pointer, as I have already told you. So, to NQ, the following steps should be taken in order to insert data into a queue. So, first of all, we need to check whether the queue is full, that means overflow condition is satisfied. If the queue is full, then we need to flash, or that we need to produce an overflow error, and we need to exit from the program, because there is no room to insert your element or to NQ your element. If the queue is not full, then we need to increment the rear pointer to point to the next empty space. This can be done in advance also. and then we need to add data element to the Q location where rear is pointing, as it is shown in this figure, that rear was first pointing towards C and then incremented to point to the next available location after checking whether location is available, whether room is available or not, and then an element D is inserted and rear is obviously updated here. So, in order to NQ, the data element is being passed into that particular procedure and it will check. If it is full, then we are going to return 0, that means we need to in a way exit from the program. If it is not like that, then we need to add 1 to the rear value, that means we need to increment the rear index, and the data which is taken as a parameter into the NQ function is placed onto that rear index of the array Q, and then finally a flag, or we can say a success indicator is returned, which is 1, which is return 1. So, in this case way we can implement NQ. Coming to DQ, accessing data from the Q is a process of two tasks. One is to access the data from where front is pointing and remove that data after the access. Now, as you can see on the screen, we have rear pointer, front pointer, and the data is always, or the element is always DQ'd from the front side. So, we are DQing this element A. So, first is we need to access that A on which this front element, front pointer is pointing, and then we need to remove that particular data from the Q. So, in order to perform the DQ operation, first of all we need to check whether the Q is empty or not. If the Q is empty, we need to produce the underflow error and we need to exit from the program because there are no elements to DQ. If the Q is not empty, then we need to access the data where front is pointing, and then we need to increment the front pointer to point to the next available data element. As you can see in this figure, front is, let us say, pointing towards the index 0, which is the first index in this array, and as we have taken out the element A which is available on that front index, we need to update that front pointer or front index to the next one. So, so we can say front will be updated to front plus 1 after an DQ operation. And if we are able to do this DQ operation in a proper manner, then we need to return success. So, the element or the pseudocode for this DQ operation is, first of all, this is empty condition is checked by using this is empty function. So, if this is empty function is returning true, then we need to return 0, signaling that your Q is already empty and you cannot DQ any more element from it. And if it is not empty, then whatever data is available on the front index of the array Q will be assigned to that element data, and then we update front as front is equals to front plus 1, and then we return that data which was earlier available at the front index, which we have saved in this data, and we need to return that data element through this procedure DQ. Now, let us say, for example, we are having an Q and we are removing some elements from the Q. So, there can be two possible approaches to remove elements from the Q. One is we remove the element from the head or the front position, and we always shift each and every element one by one in the forward direction. Another approach is we can remove the element from the head position and just move the head to the next position, as it is shown in the figure. Let us say we are having an empty queue initially, our front and rear, which is head and tail, both pointers are pointing towards the index 0. Then we inserted an element 27, as we have inserted and queued an element, tail pointer will be incremented or rear pointer will be incremented. Now we have incremented, we have inserted more elements, which are 19, 17 and 7 and some sort of more elements into that, and we keep on incrementing the tail pointer. Perfectly fine. Now let us say if we are removing the element 27 from this particular queue. So the first approach says you remove that element 27 and then 19, 17 and 7, all these elements will be forwarded to one position in the increasing direction of the queue. Or the second approach says you can just move the head pointer and you consider that particular place as blank. So 19, 17 and 7 both are all are at their own places and we have just moved the head pointer. So the idea is either we can remove the element from the head position and then one by one shift all the other elements in the forward direction, or we can just move the remove the element from the head position and move head to the next position. So considering the second approach, in which we are not updating the elements, or in which we are not shifting the elements into the forward direction, we are just updating the head pointer. So in the first, which is the A approach, in which all elements are updated one position, what is the problem? The problem is the overhead of shifting the elements one position forward, and this is going to be a huge overhead if the size of the queue is large. So we are going to shift all the elements one position forward every time we remove the first element, and also the index of element which was earlier, that means earlier the 19 was at the position 1, now it is at the position 0. So that index of the elements is also disturbed. In the second approach, when we are just moving the head pointer, we are not shifting the elements, there is no such overhead of shifting the elements. But whenever we move head one position ahead, essentially you can say after removal of the first element, size of the queue is reduced by one space each time. Let us consider this figure. So figure says 19, 17 and 7 are the three elements, tail is pointing towards the fourth index while the first element is empty and the head is pointing towards the first element. Now what if one wants to NQ an element? So NQ an element will be done at the tail position only, and we will be going in the direction after 7 and we will following that direction. So that one element at the index 0 or the space at the index 0 is kept as it is. That means the size of the total queue is reduced by 1 every time we are taking out one element. So this is a big restriction. In a linear queue, once the queue is completely full, now let us consider an example in which the queue is completely full. As you can see on the screen, it is not possible to insert more elements. Perfectly fine in this scenario. Even if we dequeue this queue to remove some of the elements, we won't be able to insert any element. Why? Because of this situation. Here we have taken two elements, but because our front is pointing towards the third element or the second index, you can say, and the rear is pointing towards the last index, we can't say that we can insert an element into it, despite of the fact that we are having this queue, we are having the two spaces available into the queue. So, when we deq any element to remove it from the queue, we are actually moving the front of the queue forward. Fine. It actually reduces the overall size of the queue, and we cannot insert new elements because the rear pointer is still at the end of the queue, as you can see here in the figure. So, in a normal queue, we can insert elements only the queue until becomes full from the rear side. But once the queue becomes full, we cannot insert the next element even if there is a space in the front side of the queue. The only way left is to reset the whole queue for a fresh start. This is a huge limitation of the linear implementation of queue, which gives rise to a problem, and the solution comes in the form of circular queue. So, what is circular queue? Circular queue is basically a linear data structure in which the operations are performed based on the basic structure of queue, which is first in first out principle, but the last position is connected back to the first position in order to make a circle, as you can see here in the figure. So, front is pointing towards the 0th index, that means no element has been taken out, but some elements have been in-queued, and the rear is pointing towards after 5 indexes, that is 0, 1, 2, 3, and rear is pointing towards the 4th position. So, this is a formation, or this is the figure of a circular queue, which you can say overcome the problems of the linear queue, that we cannot insert the elements even if the space is there on the front side. As the space is not available on the rear side, in linear queue it cannot be done, but in circular queue this limitation is removed. So, what are the features of circular queue? Actual queue data is only the data between head and tail pointers, as you can see here in the figure. In between the head and tail pointers there are 4 data items, so that is actual data. Hence, the data left outside is not a part of queue anymore. If we increment the front position, now we can say only 3 datas which are within the limits of front and rear pointers are considered inside the queue. Any data which is the data item left here is not considered inside this circular queue, only the items between front and the rear pointer. So, the other items can be considered as removed. So, the advantage here is there is no need of actually removing the data, which is I have already told you is difficult in case of, you can say, array static implementation. Only the head pointer is to be incremented by 1 position when DQ is executed, as we normally do in linear implementation of the queues. Now, head and tail pointers will get to re-initialize to 0 every time they reach to the end of the queue. End of the queue is actually the max size of the array. So, every time the head and tail pointer reach to the max size of the array, they will initialized to 0 again, as it is shown in the figure. Here tail is initialized to 0 while head is equals to 1. Also, the head and tail pointers can cross each other. Yes, this is very important. We can say, in other words, head pointer can be greater than the tail, as it is the circular queue. Here your tail is 2 while your head is 5. So, this is perfectly possible in case of a circular queue, that head is greater than your tail pointer, or your head index is greater than tail index. Now, when this situation will arrive? This will happen when we dequeue the queue sometimes, or we can say we have taken one round of the queue by inqueuing and then again by dequeuing, the tail pointer get reinitialized upon reaching the end of the queue. So, when we keep on moving in this queue, the tail pointers get reinitialized when it reaches to the end of the queue, but the head can be at the 5th position or it may be at the 7th position. So, tail is 0, but head is greater than that. So, this is also a perfectly possible situation in case of a circular queue. But the important point here is the value of the tail and the head pointer must be kept within the maximum queue size. If the maximum queue size is 7, starting from 0 to 7, so the head and tail pointer must have the value between 0 to 7. So, in the diagrams which we have seen here, there is a total space of 8 elements and the queue has a size of 8. Value of tail and head pointer will always be in between 0 and 7. When a pointer, head or tail completes one circle or one kind of, you can say, rotation after enqueuing or dequeuing, it will be reinitialized to 0. Now, how are we going to control the value of these pointers to be in the limits of 0 to max size of the array? So, this can be controlled either by checking every time whether tail or head have reached the max size, and if yes, they have reached, then setting the value to 0. Or another idea to keep this work going is to use mod operation. So, the formula to increment the head and tail pointers will be head plus 1 by mod max size, or similarly with the tail is equals to tail plus 1 mod max size. This formula will also keep your head and tail pointers within the permissible limits of 0 to max size minus 1. In order to enqueue a value into a circular queue, the function used here is enqueue. Only some of the techniques or some of the implementation statements will be changed here according to the spirits of circular queue. In a circular queue, the new element is always inserted as at the rear position, like the your linear implementation of queue, but before that we need to check whether queue is full or not. So, queue is full or not, a circular queue is full or not can be checked by using two conditions. Either rear equals to size minus 1, that means in case of 8 elements, rear is pointing towards the 7th last element and front is pointing towards the 0, that means all the elements are occupied and your queue is full. Or another situation could be rear equals to front minus 1. This comes when your front goes, let us say 2, and the rear pointer after reinitializing from 0, it will goes to 1. So, rear is 1 and front is 2. So, again in this situation you can imagine that your queue is full. So, either rear equals to front minus 1, that is also a condition of circular queue being full, or rear equals to size minus 1 along with and front equals to 0. Both the conditions will be checking whether the queue is full or not. So, if it is full, then we will display the queue is full. This is obviously as overflow condition which is discussed earlier. Now, if queue is not full, then we need to see whether this rear pointer is lying where we need to insert the element. So, we need to set the rear pointer first. So, in order to set the rear pointer first, we need to see whether it is on the max size. So, rear will be equals to size minus 1, but front should not be equals to 0. So, the condition will be rear equals to size minus 1 and front not equals to 0. Then we set rear to the 0, that is the condition of reinitialization. We insert the element and update the rear pointer. For DQ function, the function which is used to delete the element, as we have already seen, we need to check whether the Q is empty, and this can be checked by whether the front equals to minus 1, that means the Q has never been initialized, front is minus 1, Q is empty, or we need to check then if front equals to rear, they both are pointing towards one particular location, that element we are going to DQ, and after DQing that element the Q will be empty, and then we will set front and rear both to minus 1 to signal Q empty for the next operation. So, if front equals to rear, that means only one element is available. Else we need to check if front equals to size minus 1. So, if front is equals to size minus 1, then we need to set the front index as 0. We need to return the element and update the front pointer as required. So, these are the two main operations of NQ and DQ for our circular queues. Here you can see in the figure, earlier the array Q was empty, the front and rear both were pointing towards minus 1, then gradually this Q comes to the full in the fourth snapshot or in the fourth element of the figure. Then two elements were DQ'd, but as it is a circular implementation, we can again go to inserting the element onto the first position, as this is the implementation of the circular queue. All right, thank you.